Kia ora and welcome to the screencast for workshop 2 for data mining. So today we're going to be looking at pivoting data from longer to wider in order to create tables. We're also going to be looking at joins, so we'll have an additional data set on the school roll data which gives us some information about each school, and so we'll be joining that in with the student number data in order to be able to do summaries by school, for example, or by region and other things. And we'll also be looking at some data visualization, in particular small multiple plots, and then also have a look at an example on tidying some data from the Ministry of Health, or Te Whatu Ora. So we're going to start by reading in the school roll data as well as a data set on schools. So you can see that we have our school roll data here that we cleaned last time, and we've created that same data set. You'll notice I'm also loading the Read Excel package. That's because later on we will be utilising that to read in an Excel sheet from Te Whatu Ora. So that's why that's there. So when you loaded this document, you may have had a yellow bar along the top here telling you that the Read Excel library or package needed to be installed with an install button. If you clicked on that, that was the right thing to do. If you haven't installed the Read Excel package, then of course when you tried to run this code block, it would have given you an error. You can install that package just by clicking on the packages menu, clicking install, and then typing in Read Excel like that, right? And clicking install. I won't do that now because it's going to take some time. Okay, so we're going to start by looking at small multiple plots. Before we do so, we're going to take the advice written in the document and just check that we can knit this one. So we can see that there's some code running down here in the render function, and sure enough it looks fine. Okay, so we're going to start by looking at small multiple plots. So small multiple plots are where we have a chart that we've done on a set of data, and in addition to the variables displayed in the chart, so for example this one here has the number of students in each year level for primary and secondary schools in New Zealand. So this is one chart that has two variables on it essentially. We have the total number of students and we have the year level, but we have other stuff in the data, other columns in the data that we may wish to visualize as well. For example, we may want to look at this by ethnic group. So that would introduce another variable, and we could perhaps utilize something like the fill color for that, but that gets a bit messy when you have so many groups, right? We'd end up with at least 6 ethnic groups plus the international fee paying ones, so that's quite a lot of groups to be represented by color. So we could try that, right? Let's try color. So let's grab the code for the one above. Notice that I've got the data saved in the year totals data frame, which makes it a bit quicker to reproduce the chart. So what we're going to do, so there's the chart, we're going to add color to it. So if we have a look at our year totals data, at the moment we don't have the ethnic group there. So if we want to include ethnic group, we're going to have to group by that as well. So let's do that. So we're going to have to group by level and ethnic group. So now we've got totals broken down by level and ethnic group, and then we can go ahead and put that into ggplot in place of the year totals data. I'm not going to change anything at first with the plot, so we're still going to get just the total by year level. Notice that even though the total in our data was only was totaled up by ethnic group, we still got the same total heights, and that's because the different because we've got multiple rows in the data, they've all been stacked together. So the default mechanism when you have multiple rows in your data for a given year level in the total column, so we've got multiple rows for the combination of level and total, it's added them up. Okay, we can see that by watching the scale when we perhaps add the fill colour. So let's fill by ethnic group, and you can see that we get the exact same scale here. Okay. Now, of course, the problem with this is that it's very hard to compare the ethnic groups, because the orange sort of khaki-ish type colour here is actually on top of the green, which is, well, it's actually on top of this darker coloured green, which is on top of this sort of blue-green colour here. Okay, so it's hard to compare the shape. In particular, we can't really tell easily whether all of the ethnic groups have this peak in the year 7 group. We suspect that they probably do, because of course they're all accumulated, right? And so it's a bit hard to tell whether there's a peak in the red, for example. I think there might be, but you know, that bar length there and that red is not that much different to this one. So we could, for example, try altering the position. So we could use position equals dodge to dodge the bars alongside each other. Okay, that might be one way of addressing it. And now we can compare the distributions because they all start at the baseline. But of course, because the range of the data is quite different, it's actually really, really hard to see the pattern for these ones that are lower down. So it's kind of hard to compare the shape, because shape and height are both potentially different, right? And so any differences in shape might be masked by the differences in height, total number of students. Now, I guess we could get around that by converting it to proportions within ethnic groups. So we could, for example, divide the total number in each year level per ethnic group by the total number in each ethnic group in order to standardize them, right? So that they all added up to 1, across the ethnic group. So would be plotting the proportion of students at year level 1 for the European ethnic group, or the proportion of students at year level 1 for the Pacific ethnic group, and so on, right? So that would enable us to compare the distribution, because we've got rid of the scaling issue. But it's, it's another step, right? And it's also kind of looks a little bit messy, right? It's 7 colours is a little bit too many to do this type of thing. So the alternative is to produce plots just of each ethnic group by themselves. So we could do this with filter, of course, right? So that's what this next code block is doing. So here we see that the European students, okay, so we filtered down to just the European students, grouped by level, and then added them up. And the same with the Asian students, right? So we can see that they do have different shapes. But we want to do this for all groups, right? And display them simultaneously so that we can compare them. And, that's going to end up with 6 charts, which we could sort of somehow print on the same page or something, but it's going to be a bit messy. And of course, the ggplot function has, the ggplot package has the ability to do that via facet wrap. So this code down here, we note that we've grouped by ethnic group and level, like we did earlier, in order to compute the totals by level and ethnic group. And then instead of using the fill color, we've added this extra line for faceting. So facet wrap basically gives you divides the data by the variable that you supply, in this case ethnic group, and then does a 1 chart per ethnic group. And so we get this chart here. So you can see now we've got all of them, right? So this is that European chart that we did before, this is the Asian chart that we did before, but now we've got the other groups. Okay. Now, we still have a problem with the heights here, right? In that everything's been put on a common scale. The advantage of that is it's allowed us to squash the graphs closer together, right? So more of the page, if you like, has been dedicated to the data rather than the than the scales, but that has meant that we've had to use the same scale. Which is probably not ideal in this case. Again, we could, divide, switch each of these from counts to proportions within each panel, and that would solve that problem. The other way we could do it is switch it so that each chart had a different Y scale, which is probably a little bit more useful because the total number of students is useful in and of itself. So let's try that. With the hint, we could have a look at the help. Let's grab the code first and reproduce the chart. There we go. And then we'll just put the cursor on the facet wrap and press F1 to get the help. Okay, and if we look down here, we have a parameter called scales. If we read about that, should the scales be fixed, which is fixed to the default, free or free in one dimension? Right, so that suggests that we probably want to go scales free. Now, there's not really an advantage to freeing up the scales in the X direction because the scale doesn't really change that way, right? So some of them, if we did do that, then some of the groups potentially don't have any students in that category, and therefore the X-axis would change, which probably is not what we want. So we just really want to free up the Y scale. And you can see now it gives us each of the panels on a separate scale for Y, and we can more easily compare the groups. The distribution, right? So we can see that there is actually some variation in the distribution. It's not massive. So the European, for example, has this increasing trend earlier, as does Pacific and Māori, and well, that's probably it. Asian seems to be a little bit flatter, but there's always that peak at year 7, and then the decline afterwards. The extent of the decline differs by ethnicity at least a little bit, right? And then we have this quite different shape for the international fee-paying students, of course, because these are folk coming from overseas to study in New Zealand, which tend to be college students. Okay, so redoing the plot without those students might be useful. Let's try that. So let's grab our data and filter out such that the ethnic group is not international fee-paying. We'll check that makes sense. Yep, looks as though it's done the trick, and then we can pipe that into ggplot. There we go. And now that we have a sort of a grid, if you like, of points, we could experiment with the number of rows and columns. So we could try 2 columns. Okay. You could even try 1 column. Okay, you'd probably need a sort of a more vertical orientated chart. You can do that. So fig.width and fig.height can be used inside this. So there's some options that you can give to the R code chunk, which are done inside these braces up here. These are in old-fashioned units known as inches, I believe. So let's perhaps do a 7 by 10. There we go. Right, so you might want to do something like that. The advantage of this type of setup is that the scales, we've got none of the X coordinate, if you like, has been chewed up by an extra scale because we just need the 1 now on the left. Okay, perhaps that was a little bit too big. Perhaps we can scale it down a bit. There we go. Okay, you can feel free to play around with that if you wish. Okay, so that's small multiple plots. We'll look at another example further down. Now we've got data on schools. So this has 1 row per school. The school name is the same as the school name in the role data. but we have a bunch more information. So we know whether it's the sector, whether it's a primary, composite or secondary school. There's the type, which contains a bit more information about it. So we've got full primary, contributing, composite, various other things. We've got whether it's a state school, a state integrated school. We've got the school gender. We've got affiliation, so we've got some context of whether there's affiliation with various things. We've got some information on that affiliation, some information on Māori affiliation. Regional Council, Territorial Authority, and Takiwa. So Takiwa is I think it's 3 or 4 regions in New Zealand in which the spatial regions in which the schools are collected. So if you like, it's a broader regional specification than the Regional Council or Territorial Authority are. So all 3 of these variables are spatial information. Okay. We also have EQI, which is Equity Index, and that's sort of about 2 or 3 years ago, and for a long time before that, schools were classified into deciles, based essentially on the communities from where they draw their students from, so that the funding for schools could be adjusted in an equitable fashion. Essentially, more funding was given to schools that were drawing students from areas that may be deprived in other ways, such as low access to healthcare and things like that, to try and sort of provide some balance to the education system. That has been replaced with this new thing, the Equity Index. I suspect that you can probably just divide the Equity Index up into 10 groups and you'd get something very similar to what we had before. But there you go. So let's answer some questions. How many schools are there in the Palmerston North Territorial Authority? So the first thing to do is to recognise what column I'm going to be using, and helpfully it's right on the screen here, Territorial Authority. So we can go schools, filter, Territorial Authority is Palmerston North. Okay, and we can see that there are 43. So here's another one. Of the schools in Palmerston North, how many are co-ed, single-sex schools or single-sex boys' schools? So again, we could grab our schools from Palmerston North, and then we could do this multiple ways. So we could just have a look through the data. So here's the school gender, right? It's all co-ed in the first 10. It's all co-ed in the second 10. We've got 1 single-sex boys, 1 single-sex girls in the next lot. All co-ed, right? So there's only 1 single-sex boys, 1 single-sex girls school, which are Palmerston North Boys High and Palmerston North Girls High, and the rest are co-ed, right? How could we do that with code? Multiple ways. We could group by the school gender column and then summarise the number of rows, right? Okay, and the third way we could do this is use count. Right, so count basically does the group by summarise for us because it's such a common operation. Okay, produce a chart that shows the breakdown in secondary schools by school gender for each of the 3 takiwi. So we need just secondary schools. So how are we going to get that? Let's have a look at the data. Okay, so we have sector. I think it's probably what we want. Let's check by counting that column. Remember, a good way to find out what's in a column is to count it. There we go, that's what we want, I think, because then we can get our secondary ones. So we're going to filter sector is secondary. Okay, that looks to be what we want. And then we want to break down things by school gender for each of the 3 takiwi. Okay. So let's go. We want to group by the school gender and takiwa, and then we want to count the number of rows. There we go. So we can see that for each of the 3 takiwa, we have the counts of co-ed schools, single-sex boys schools, single-sex girls schools. We also have one that's that the senior school is co-ed, but junior is boys. Or actually, we've got two like that by the look of it. So perhaps we may want to remove those. So let's add another filter. To get the spelling right here, given that it's got some punctuation, I'm going to copy and paste. There we go. We've only got the 9, and now we can put that into ggplot, into a column chart. So X is going to be the school gender. Y is going to be the count. Okay, that looks right. And then we want to do that per takiwa, so that we can facet wrap by takiwa. So there we go. Given the length of the labels, we might even consider flipping this around maybe. So I'm tempted to try swapping X and Y. Maybe. I think if we do this, we probably want to do just a single column. There we go. I like that a bit better. We can easily read the labels. I'm not going to overlap. And then we can compare the distribution. In particular, we see that in Te Tai Ronga and in Te Tai Whenua, there are a higher proportion of single-sex schools compared to Te Tai Raro. So that's potentially interesting. Okay. Right, so that's the schools data. Now we're going to join this onto our clean student role data with a left join. So you remember a left join takes rows for each row in the left-hand data set. So in this case, that's going to be the clean data, which is our school role data. So each row is the count of students of in a particular school, level, and ethnic group. We're going to join that to the schools data. So in this case, the common variable we're going to join on will be school, the name of the school, and then the other information that we have for each school is going to be appended into that data set. So you can see that it's joining by school, which is what we would expect, and that now, in addition to the 4 original columns, we now have columns on information at the school level. Okay. Okay, so let's answer some questions here. How many students are there in each regional council? So this is the advantage of joining the student-based data to the school-based data, is that now we can answer questions about at the student level using broader information like the regional council, for example, right? So we're going to use all our data, and then we're just going to group by the regional council and add up the number of students. Okay, so you can see that there's 64 students in the Chatham Islands. Obviously, most students, 284,000, are in Auckland, and so on, right? Okay, How many students of each ethnicity are there in each takiwa? So we're going to group by ethnic group and takiwa, and then summarise number of students, right? And we get that breakdown. So for each ethnic group and in each takiwa, we have the total number of students. Okay. What about schools with a religious affiliation? Okay, so the first thing is to find what we need, right? So one way is to look at the names, right? That'll tell us the names, and we can see that we have 3 columns with affiliation. So we have affiliation type, affiliation, and Māori affiliation. So we might want to try just counting some of these. So let's just try affiliation. Okay, this looks like some of these are look as though they are religious, right? We've got Anglican, Baptist, Hare Krishna, and so on. Some are not, so I don't think Montessori is associated with religious. We've got Māori Trust, that's not religious, so okay, so that's not quite the one we want. So let's try affiliation type. There we go, right? So we just want the ones with religious affiliation, so now we can just switch that to a filter. Okay, and then just add up the number of students. Okay, so 116,000 students are in schools that have some religious affiliation with them. Okay, in this last one, produce a chart showing the total number of students for each year level within each takiwa using facet wrap. Side-by-side plots by takiwa. So you remember the key is to get the data in the right form first. So first we need the total number of students for year level and takiwa. So we're going to group by takiwa and year level. Okay, and then we're going to summarise total number of students. Okay, so Te Tai Raro, we've got year level 1 through 15 and the number of students, Te Tai Ronga, and so on, right? Te Tai Whenua, same. So now we can throw that into ggplot and do our normal column chart. So X is going to be our level, Y is going to be our total, and we're going to get a column chart. Right, and then we're going to facet that by takiwa. Okay. So we see that there's more year 14s and 15s in Te Tai Ronga compared to Te Tai Whenua, which I believe is the South Island, and Te Tai Raro, which I believe is Auckland and north of there. So this is basically the Waikato and all the way down to Wellington. I'm not sure if it includes Wellington or if Wellington's in with Te Tai Whenua, but this is basically south of Auckland, essentially, in the North Island, I believe. Otherwise, the pattern seems largely similar. Slightly more students in Auckland and above. Okay. Again, this probably is fine as it is, but we might consider switching this round so that they're stacked if we want to, but I don't think that's really necessary in this case. Okay, so this is faceting by one variable. Often we might have 2 that we might want to do. And so you can see here that they've all been placed into one row. And so you could see that if I had another variable here, I could potentially use that to split it into columns as well, thus forming a grid. And that's exactly what facet grid does, right? So for example, we could alter the above plot to include ethnic group as well, right? And we'd have a rather large set of plots where we've faceted by both takiwa and ethnic group. So you can see all the way along the top here we have Te Tai Raro, right? Because I've chosen to use 6 columns and there were 6 ethnic groups, I filtered out the international fee paying group. You can see that they all fit along there. So this entire top row is Te Tai Raro, then this row is Te Tai Ronga, and this row here is Te Tai Whenua. Similarly, this column is Asian, this column is European, and so on, right? So the The rows are the takiwa and the columns are the ethnic groups. So facet grid basically formalizes that idea and forces it to be that way, right? If I chose a different number of columns, like 4 for example, then I would get the same set of plots, but of course they're distributed a bit more oddly, right? In that I've got some of the Te Tai Raro in row 2, and the Te Tai Runga go over 2 rows, and so does the Te Tai Whenua, right? And each ethnic group is no longer in a column. So there's advantage to having things in rows and columns. So let's switch the above plot to facet grid. Right, so all I'm going to do is change this to facet grid. So facet grid, if we look up the help, takes a rows and a columns. Right, so our rows are going to be our takiwa, and our columns are going to be ethnic group. Notice the use of the vars helper, so that we're pulling the name there out of the data frame. Right, so the vars helper works a bit like AES does, in that it allows ggplot to go into the data to pull the variable out. And there we go. Right, so you can see that this is actually a little bit better than this one, in that the way because Te Tai Raro is the same all the way across the row, we can actually utilize a little bit of space on the end for that label, which then gives more height available for each of the plots. Okay, so it's a little bit more efficient. Now, the disadvantage with a grid is that you're only allowed a single y-axis per row and a single x-axis per column. Right, so you can change the y-axis for each row, but you can't allow the y-axis to change by column. And partly this is just due to space requirements, right? So if you took all the space taken up by this axis here and you replicated it all the way across, you're going to run out of space for the data, right? And so it's kind of enforced that you only have axis labels along the edge, which means that it must be the same across the row, and the x-axis must be the same down the column. So that's a bit of a hassle when you have data that has multiple heights to it, like these data do. Okay. So we do have the scales parameter that we can play with. So for example, we can go scales equals free y, just like we had before. But you'll see that it won't actually change things very much. Okay. So it has changed the scale. So this top row has a different maximum, only goes up to 10,000, whereas this one goes up to 15,000. But it hasn't solved the problem of the different counts, because again, the different counts are going across, like each of the columns have a different count, is the problem here. So one way to solve this would be to switch the role of the rows and the columns. So instead of having ethnic group in the column and takiwa in the row, if we switched it around the other way, then ethnic group would be in the rows, and therefore we could assign a different scale. Okay, so that of course is easily done just by swapping the role of rows and columns. Right, so let's do that. Then we'll get rid of the scaling just so we can see what the difference is. So in terms of the rectangular grid, it's not quite as ideal, if you like, because we've sort of got a landscape figure. But it's not too bad. But now you can see that we can easily change the scale of each of these here, which would then allow us to visualize the shape. So we could add scales equals free y. Okay, and that then gives us a better representation perhaps of the data. Right, we're not so dependent on raw counts. So now you can see whether there's different. You can better see differences between the pattern. Now there is some differences, obviously, between Te Tai Raro and Te Tai Runga and Te Tai Whenua, but you can see that they're very dependent on the actual ethnic group. So for example, Te Tairaro, which is Auckland and above, includes a higher number of Asian students compared to the other two groups, and also a higher number of Pacific students compared to the other two groups. Te Tai Whenua contains more Māori compared to the other groups, and so on, right? So interesting to see how the distribution of ethnic groups changes in space over time, right? Well, we don't have a time aspect, but changes in space, right? So these are geographic sort of centers for different populations, right? Okay, so the next thing we're going to do is look at tables via pivoting. So pivoting is where you take data that is in one particular form, such as being long form data like we've been seeing here, and you convert it to be wider, which is often more useful for humans to read. So in general, long form data, so that means data that is tidy, so each row is an observation, each column is a variable. That data is good for data processing, it's good for charting, it's good for summarization, okay? But it's not necessarily good for reading, right? So for example, we had this one here, okay, where we computed the number of students by each ethnic group in each takiwa, okay? Now the problem with this is it's kind of hard to read for humans, right? It's entirely processable. It's perfect for doing a chart, okay, because we've got a single column for the number of students, but it's hard to compare, for example, between the takiwa, because, for example, I have to compare the first row with the eighth row, with the, I guess this would be the 15th row, and they're far apart, so hard to compare the numbers. But actually, there's just counts by two variables here, so we could set this up in a grid, in an array, where the takiwa, for example, are the columns, and the ethnic group are the rows, and we then have an array of counts, allowing us to easily compare. A bit like we did up here, right? We can easily compare this because it is in sort of a matrix or an array. So we can compare across the rows and down the columns quite easily. So to do that, we pivot wider, okay? So we take that same data, ethnicity by takiwa, and we pivot wider. So when we pivot wider, we need a column to take the new column names from. So in this case, we're going to be taking the new column names from the takiwa column. So we're going to end up with columns for Te Tairunga, Te Tai Whenua, and Te Tairaro. And then we're going to take the values to fill those column names from the students column. So we're distributing the students column across the takiwa, the new takiwa columns that we're creating. And this will then compress down the number of rows because the ethnic group, the only remaining data, is then replicated. So let's see what it looks like. Okay, so we have a much sort of nicer, cleaner table here containing the same information, right? We haven't lost anything, but now it's in a form that's easier for us as humans to read. The disadvantage is that now it's harder to process, right? If we wanted to, for example, compute the total number of students in Te Tairaro, and this was the data we had, we'd have to summarize and sum across that column. If we also wanted to summaries across this column and this column, we'd need to do 3 separate sums. Whereas if it was of this form, then all we need to do is group by that variable, the takiwa variable, and compute the summarize, right? So we could do it all at once. So that's the advantage of long form data. Wide form data, main advantage, easier for humans to eyeball it. Okay? Right, let's do some examples. Create a table with the total number of students for each year level in each takiwa. Okay, so same idea, right? We're going to group by takiwa and year level. Summarize number of students. Check that we've got what we expect. So yes, we've got 45 rows, which makes sense. 3 takiwa, 15 levels, 3 times 15 is 45. Number of students looks about right. Now let's pivot wider. So again, the names are going to come from our Takiwa column, and the values are going to come from our total column. Okay. So there we go. What about the next one? Create a table with the number of each ethnic group in each year level. I think this means the number of students in each ethnic group in each year level. So otherwise the answers are fairly straightforward, aren't they? So again, we're going to group by ethnic group and year level, and then summarise the number of students. Okay, 105, 7 times 15, that sounds right. And then pivot wider, names from the ethnic group, values from the level. Oh, values from level, that's obviously not what we want, is it? Values should come from the total column. That's better. Okay. What about adding totals? So let's go back to the ethnic group by Takiwa table, which is this one here. Oh, ethnic group by Takiwa, that was this one here, wasn't it? So here we go here. So what if we wanted to add a total column here? So a total column would have to add up these entries here, wouldn't it? So there's a bunch of ways to do it. So the first method is to just add a new column. We do that with a mutate. The new name of the column is going to be total, right? And that's going to be Te Tai Raro plus Te Tai Runga plus Te Tai Whenua. Oh, I typoed that, didn't I? There we go. So let's make that a little bit wider so we can see it. There we go. Okay, so you can see that that's correctly added up across, and we've got our totals. Now the disadvantage with this, need to know the names of the column. I typoed. Not extendable later on. So I can just imagine that in a few years' time, the Ministry of Education is going to decide that perhaps the Te Tai Raro or Te Tai Whenua groups are getting a bunch larger, or perhaps Te Tai Runga, that's the one that I think might be, well, they're similar in size. These groups are getting large, and so they may want to split them, right? And as soon as they split them, they have to introduce a new group, and now my code is broken, right? So this same code will probably work next year, and probably the year after, right? All I have to do is update the original data set with the 2024, 2025 data, 2026 maybe is going to work, right? And everything will be hunky-dory. All my code will work and I'll get the same answer. But then 2027, they suddenly change the Takiwas, and now the code breaks, right? But I might not even know it breaks, right? They could perhaps introduce a new one, keeping the other three, right? So they split, say, Te Tai Runga into two, and the north part of Te Tai Runga stays as Te Tai Runga, and the south part, they introduce a new one. Under that case, I wouldn't know that my code's broken, right? So the code would still run and give me an answer. It's just it's now missing a bunch of students because I haven't included those students in my total. So I'd have 4 columns here, but the total would only be something over 3 of them. Okay? or if the takiwa names change, right? So you can imagine that that might happen if one of these names was supposed to have a macron, for example. In the first year that the data was collected, they mistakenly didn't put the macron in, right? And so I'm not using the macron here because that's what the data told me, and those are the columns I need to add up. But of course, next year's data, when they correct the macron, this code again isn't going to work. It's going to fail in that case because one of these columns won't exist, right? The correct column will have a macron, right? So I will be broken. So the sort of better method is do the totals while the data are tidy. Okay, so let's do our computation again. Well, let's keep things the same. Oh, I actually used students above, didn't I? So let's do the same thing. All right, so there's the data in tidy form, right? At this point now, we could group by ethnic group and do our totaling. Right, so the first summarize here is summarizing by takiwa and ethnic group, right? That's not quite what I want to do. Let's stop that. Let's comment both these out for now. Let's figure out what we need to do. What we need to do here is add a new column for total, right? So summarize won't add a new column, it'll replace existing stuff, right? It'll only show the columns that we have. So instead of a summarize, we want to mutate. Okay, so the first summarize is computing the number of students. So that's per takiwa and ethnic group. The second, the mutate then, is adding up the within ethnic group, it's adding up the students column. So this 139,908 is 84,000 plus 34,000 plus 21,000. Right, it's 139,908. Okay, so now that we've got the data that we want, so we can then pivot wider. Right, so names come from our takiwa, our values come from our students column, and there we go, we've got the table. Now the only disadvantage is the total column here is on the left, okay, but we can put it on the right. So a handy function for that is relocate. Locate it after the last column. Okay, now notice that in this code here, we haven't once used the name of the takiwas. So this code is still going to work even if they change the name of the takiwas or if they add a new one, right? Code will still work. As long as the column names and so on stay the same, the code will still work. Now it's a little bit messy because I've got two group bys. Part of this is because of the order that I did the group bys in. Okay, so it matters only a little bit. So the reason that I had to do this additional group by here is because after the summarize, I was grouped incorrectly. So let's check this, right? So group by Takiwa ethnic group, summarize the number of students. We're now grouped by Takiwa. So what's happened in the summary, and it's even told us, summarize has grouped the output by Takiwa. Okay, it was initially grouped by Takiwa and ethnic group, but the summarize then ungrouped. And it did so by removing the innermost group, the ethnic group. Okay, not the outermost group, the Takiwa. So it got rid of the ethnic group because within Takiwa, there was only one row per ethnic group. So you don't have to bother grouping, right, if there's only one row. The reason for grouping is if there's multiple rows that you want to process at the same time. So a better way of doing it, a better way to do it would be to group it the other way around, right? Because what we want to do is we want our mutate to then run by ethnic group. So if we swap the order of these, then when the inner group is removed, it'll be the Takiwa that's removed and will still be grouped by ethnic group. Right, so now we're still grouped by ethnic group, and so we don't need to group by ethnic group because we're already grouped by that, and we can just run the mutate directly. And get the same answer. Okay, so thinking a little bit about the way you group can mean that you don't have to additionally group things. Now, there's a slight disadvantage here in that when I'm reading this code back, I need to be aware that the mutate is being done within the ethnic group grouping. And that's not necessarily obvious from the code. Whereas here, it is obvious because the very previous command was group by ethnic group. Right, so this might be a little bit simpler. We've eliminated a step, but the added complexity is that when we read it back, we've got to remember that that's how it works. Okay, and as long as you remember how that works, then that's fine. So there's actually nothing wrong, of course, to keep this line in here. So we could put that in there if we wanted to. Right, it's already grouped by ethnic group. Regrouping it by ethnic group is not going to make any difference, but it's optional. Okay. Right, let's have another one. Try creating a table with the percentage of students of each ethnic group within each Takiwa. Right, so instead of the totals, we want the percentage. So again, computing the percentage, we want the percentage of students of each ethnic group within each Takiwa, right? So that they're going to add up to 100% for the within Takiwa. So let's think about this. So we're going to want to group it by Takiwa because that's going to be the thing that we compute the percentages on. Then ethnic group, right? So that gives us our totals, and now we're grouped by Takiwa, and so now we can compute our percentages. All right, so we're going to do a mutate. Our percentage is going to be students divided by the sum of the students times 100 to get percentages. Okay, maybe we want to do some rounding. I suspect 100 was rounded there. Let's just put the round here like this. Maybe there we go. Okay, So you can see that these percentages within the Te Tairaro add up to 100. So and now that we have the percentages, we can create the table, right? So just noting again that this is grouped by takiwa. Okay, so you could have the group by there if you want to help explain your code. Let's maybe leave it in this case. Okay, so now we just have to pivot the percentage wider. So our names are coming from our takiwa, and our values are going to come from our percentage. Okay. Now this isn't quite what we want, right? Notice that we get this bunch of NAs. It hasn't compacted things down like we might expect, right? So it's correctly pivoted things. So the percentage is now in the corresponding takiwa column, but they haven't been compressed up. And the reason they haven't been compressed up is that the rest of the information for each row wasn't compressible, right? So the other information associated with the 26.3 was these two pieces of information. So the ethnic group is Asian, number of students 84,000. With this one, it's again Asian, but a different number of students, right? Now, of course, we don't need the number of students, but it's because the number of students is different that we can't compress up these things. So if you pivot wider and don't get a nice compressed chart like you might expect, it's because you've included something that you don't want, right? So here we want to get rid of our students column. Then the pivoting will work. Okay. Okay, and the last little exercise is looking at cleaning data, right? So we're going to use some data from Te Whatu Ora. So let's go and have a look at it. Okay, here it is here. And the particular data set we're going to look at is, let's have a look. I think it's down here. So here we go, 3-month reporting period. And we're looking at a particular one, which I think it's this one. Let's have a look go back and have a look at what's it say? It says 1st of July to 30th of September 2021. 1st of July, this one. So let's have a look at that. So when we load it up, we can see that we get this very pretty looking spreadsheet. So this is clearly a spreadsheet that's been designed for a human to look at and not being designed for a machine to read and process. Okay. Whenever you see colour in a spreadsheet, it's for the purposes of a person, not for the machine. Now, in theory, when we load that data into R, the colour information of the cell can be extracted, but it's very hard to do so, right? If you like, that's a completely separate channel of information, right? It's like another dimension. In each cell here, we have the number, but we also have other information associated with the cell, such as the text formatting, the background color, the foreground color. There's lots of other stuff that could be associated with that cell. But usually the only information that's important is the number, right? The value in it. And so whenever you use things like conditional formatting or different text colors and so on to distinguish interesting things in a data set, that's usually not visible at all to a processing chain that comes later that's machine driven, right? That's run through a tidyverse pipeline, for example. The better way to associate information with cells that is important information, the sort of thing that you might want to highlight with a different color, is to add another column, right? And point out what you're highlighting using that additional column. Then that additional column, of course, is available to read in to any processing code. The other thing we notice is that this is clearly wide format, right? And that we've got a variable across the top here, which is ethnic group, right? So we've got other Asian, Pacific, Māori, and New Zealand European. There's no Mila in this data set. We've also got totals. So this green block here is just the sum of these other ones, so that's completely redundant information. We've also got the number eligible and the number fully immunised, and then a percentage. And that percentage is actually stored as a number. It's not a formula, right, associating these two numbers. So this is just 36,359 divided by 43,277 times 100%, and then rounded, or in this case, by the looks, not rounded. Okay, so that's, all of these columns are redundant information. Again, useful for perhaps for a human eyeball, not useful at all to a machine. We've got a bunch of information in the spreadsheet at the top, which is not useful. We're going to skip over that when we read the data in. We've got two rows being used for headers. That's non-standard. Normally you would only use one row for your header data. We can see that the information we need is actually in the top row, but we also need the information underneath. So we need to somehow combine these two things. That's annoying. What else we got? Let's have a look and see. There's a bunch of junk down the bottom. So if we read this spreadsheet in without accounting for that, there's going to be a bunch of extra junk down the bottom. This stuff is in this column, which is the stuff that's useful, the milestone age, but we're going to have some junk in it. We're also going to have some junk here, which is going to be in this column here, column C. Right, so that's going to be messing column C up. We also have total rows. So we've got a national total here. We've got another total here, which is a total of a total or something. Who knows exactly what that is. So lots of problems with these data. Okay, 54 months hasn't been copied all the way in, although I think maybe they've done a merge cell here, which means that 54 months is actually filled in all those cells. It's just only shown in one of them, I think. So, lots of fun things for us to process in order to get it into a usable form for us to do some analysis. Right, let's have a go at reading the data in. So we're going to download the file directly off the web with download.file. It's going to be written to your current working directory as immunization, and then we're going to read it in. Okay, so this is what the data looks like. Okay, basically junk, right? We have we've got a bunch of names which are meaningless. So these are the names. We've got this name here. That's the name of the first column. The name of the second column is ... 2, and so on. So those aren't very useful. Essentially, it's junk. And the reason is because of the junk that was at the top of the file. Okay, so we can get around that by skipping the first 3 rows. So if we skip the first 3 rows with the skip function, skip parameter to read Excel, we get something a little bit more useful. Okay, so this is now getting somewhere. We notice that our we've got the milestone age there. Notice the typo, millstone. Anyway, we've got DHB of residence, which is useful. We've got eligible, although the naming of it isn't ideal. We've got fully immunised and percentage, but then we've got another eligible, fully immunised, percentage, and so on, right? Because we haven't been able to pick up that these represent different ethnicities. So things are better, but not great. Now, to simplify things, we're only going to look at the totals. So only going to look at these first 5 columns, and we're going to ignore the ethnicity breakdown stuff that came afterwards. So when we simplify things like that, we know we only have to search for 5 columns. We can do things like rename these columns to useful things directly. So that's what this next code is doing. Right, we're taking the immunization data and we're selecting out just the things that we want and renaming them at the same time. Now, this isn't particularly necessarily the best thing to do. So I've ignored the names that are in here already, and I've referenced the columns by position. Usually that's okay if the data that you're getting has a consistent format. Now, that's not always the case with this particular data set, this immunization data set. You could see that on the web there were hundreds of the things, and they've changed over time. Okay, so the layout has changed over time. If we have a look at the latest, for example, what do we got here? You can see that, whoops, that's Discord. You can see that we've got way more information at the top, and now we've got different DHBs, but the actual the layout in terms of rows is actually pretty similar. Oh, well, actually, no, it's not, is it? So previously we were taking the first 5 columns. Now we'd have to deal with the fact that we've got the district of residence. So this is the DHB information. That's now been broken down into the main new Te Whatu Ora groupings. DHBs have been got rid of and they've been replaced with broader spatial groupings. So the code that I have ain't going to work on this one, right? So always be aware that naming things, referencing things by column number might mean that things break. Now, of course, referencing them by column name would also mean that things break because the column names change. Okay, so, to a certain extent you can't win. So you just sort of have to do the best possible. But now we've got something that looks pretty good. Okay, but there's some other stuff we have to get rid of, right? We've got some total rows. This one here is a total row as well, isn't it? Total of what, I'm not quite sure, but anyway. So let's do some filtering. So first of all, we can filter this one out. Okay, we can filter the national total out of the DHB column, right? And then we can have a look and see what we're left with. So part of the way we can have a look and see what we're left with is to count the various things. So for example, we could count the milestone column and count the DHB column to make sure that we have consistent things, right? So we should have a row for Auckland repeated for each milestone. We should have a row for milestone repeated for each DHB. So the number of times we see milestone in the data, each milestone in the data should be the same. So you can see that that's in fact the case, right? So that's looking quite good. So we can see 20 of each, presumably corresponding to 20 DHBs. And then if we have a look at the DHBs, we see 7 of each, all the way down, corresponding to the 7 milestones. So this hasn't actually been too bad, right? We've managed to get the data into shape quite quickly. One thing we do notice is that the eligible column has been interpreted as a character string when we know it's not a character string at all. So part of the reason for that is we've got this milestone stuff here down the bottom, the extra junk that was down the bottom, and the comments were in the eligible row. So when the readXL package read these data in, that column was interpreted as being character strings because it had some text in it down below the numbers. Okay. Now, we've managed to filter that out, although we filtered it out without really knowing it. Okay, so that that information isn't actually in the clean one here. Let's have a look at that one. So now we've only got 140 rows and we don't have those notes in it. So where did they go? So And the reason is a bit subtle. The reason that we lost those rows is due to the DHB column. Okay, so we filtered out anything that wasn't the national total. We filtered out such that we only retained the rows that weren't national total. If I get rid of that, so let's comment that bit out and just filter by milestone and have a look at that, then we can see that we still get the notes there. Okay, but when we filter and include this thing to get rid of the national total, we've lost it. We've lost those key rows. And the reason is, of course, that DHB for those key rows was missing. It was NA. And it turns out that the not equal to filter ignores NA. So not only has it filtered out the national total rows, it's also filtered out the NAs. And that's important. It's something that is often goes under the radar, and sometimes it's easy to miss. That whenever you do a filter on a column that has NAs in it, depending on the setup, the NAs may also disappear. Simply because, if you think about it, it's comparing NA to national total, right? It's saying, is this thing that I don't know what it is equal to national total? And the answer, of course, is I don't know, right? Because the value for DHB for that row is not available. So it could be national total. We don't know, or at least the computer doesn't know, and so it gets rid of it because it's not sure. So filter by default, if the comparison turns out to be NA, it will drop it. So it's just important and something to know that when something goes missing and you don't expect it to, particularly if it was a missing value or something, it might be due to a filter. Okay, so let's write some notes about this. The DHB does not equal national total line has filtered out the cases where DHB was NA. This happens to correspond to the rows we want to the right. Okay. Right. So the last thing then is that we still haven't fixed this eligibility thing. So we could switch that now to numeric, right? So this is this last line here. Okay, so it's converting it to numeric. And now that we've got that numeric, what we could do to validate the data is just check that the proportion column is correct, right? Because we know that this is just computed from these two. So we could compute it ourselves and then check, right? And that's what the code here is doing, right? So let's have a look, see if we can understand the code, right? We're computing a new column prop check, and then we're comparing them across. And I'm not comparing them with equality, right? Because things might have been rounded, right? So the proportion here was stored as a double precision number in the Excel sheet, and it may well be that it was rounded in that process. So let's check. Let's just check and see if there's anywhere. Yeah. So if I just do not equal to, then I find 18 rows where the proportion and prop check are not the same. So the indication is that the proportion stored in the file is different to the proportion computed from eligible and immunized. But you can see, looking at them, eyeballing them, they look the same, right? And the reason is that the proportion is just like, these are accurate, but only accurate to so many decimal places due to rounding, right? So this is what this ABS stuff is doing, right? So if we compute that, that'll just be the difference between these, which is going to be something really close to 0. We then take the absolute value of it to make sure it's a positive number, and then we're checking if it's bigger than 10 to the minus 6. If it's smaller than 10 to the minus 6, then we throw it away. And we get no rows returned. Okay? So the proportions are accurate. So we've cleaned a set of data. Our goal now is to reproduce a plot, right? So what's the plot we're reproducing? It's this one here. Okay. So you can see this here is a chart of immunised for different milestones. So we've got 6 months, 8 months, 12 months, 18 months, 24 months, 54 months across the different DHBs. Okay. And your goal is to see if you can reproduce that chart. So have a go. I'm going to have a go here and see if I can do it. All right, so what are we going to need? Let me think. Let's have a look and see what our data looks like. Okay, so we're looking at the proportion immunised for a start. So we're going to have the proportion by DHB and milestone. So it should be straightforward. Just throw that straight at ggplot. Right, so our x-axis is going to be our proportion. Our y-axis is going to be our DHB, and we're going to be faceting by milestone. And we're going to be a column chart. There we go. Practically done already. Right, so now I just compare my chart to the one that I want and fix up stuff accordingly. Right, it's a matter of slowly working piece by piece on the chart to adapt it to the right form. So the first thing I note is I've got 7 panels. And this one only has 6. This one doesn't have the 5 years. So that's easy. I can get rid of the milestone 5 years. Much nicer. What else? The second thing I note is that the order of the facets is different. So this is in 6, 8, 12, 18, 24, 54. So this is in order, whereas mine is not. Mine is in alphabetic order. So I need to reorder it to put the 6 and the 8 first. So there's a wee hint about the re-level command. So if we have a look at the help for the re-level command, right, you can see that it takes a factor and then takes a bunch of levels, and you can specify which ones they go after. So I am going to factor re-level. I'm going to re-level the DHB. I'm going to reorder the milestone such that 6 months and 8 months are first. And then I get things in order. So I didn't have to order the other ones because they were already in order. All I had to do is move the 6 and the 8 to the front. Okay, and by default you can see that it puts the levels that you specify after the 0th entry. So it puts them first. Okay. Nice. What else? Well, we've got different colours here. So different colours. So it's coloured differently based on whether they're meeting the 95% target. So we could introduce a new column, which could be, it's 90% by the looks. Is it 90%? 90%, yeah. So met target would be if the proportion is greater than 0.9. All right. So most of the time that, did we meet the target is false, but every now and then it's true. And then we could colour by that, couldn't we? Or we could fill by whether we've met the target or not. There we go. That's looking right. Okay, obviously the colours aren't right, but, we'll get there. What else? The order of the DHBs is different. They're in reverse. So let's reverse the DHB factor. That's better. We're pretty much there, aren't we, really? You've just got to get the colours right. What else? I've got a vertical line here, so that's at 90%. So how do I do a vertical line? My suggestion is to Google it. Vertical line ggplot. We want a V-line, which takes an x-intercept. It's going to be at 0.9. Perfect. Now is the line over the top or behind? I think it's behind by the looks. So we'll just change the order of these two. That's better. It looks as though we have, so let's get the colours right. So what do we need? We need to change the scale, colour, no, fill, manual. And what do we want? Oh, it tells us what they are. So we want pink. And grey. Perfect. It's looking pretty good now. We've got a different theme. Let's have a look. What's the theme there? Chart uses theme minimal. Okay, we're super close now. What else? We've got to get rid of this guide here. So to turn a guide off, we use guides. Fill equals none. Nice. What else? We've got some labels. So we've got no DHB label, and we have % immunized along the x-axis. So y is null to turn off the y label, and x is going to be % immunized, percentage. Perfect. And now we need this in %. So Google, how do you get a percentage? You do it by altering the scale. So you can go scale x continuous, because it's a continuous scale, right? That's the difference. So all the scale functions, so things for altering the x-axis scale, the y-axis scale, the color scale, so legends and so on, is all the scale function. So this is altering the fill scale, this is altering the x scale. It's continuous, and then we want our labels to be done with the %. I think it's like that. Is that what it is? Label % maybe? Oh, that seemed to work. Nice. The other thing is that they all go up to 100%. So limits 0 to 1, I think. There we go. Got it up to 100%. And we're basically done. The only difference now between this chart and this one is things like the size of the font. Okay, and that's going to change with the size of the figure. So for example, if I make the figure width 10 and the figure height 8, I think the defaults are 7 and 5, then the font size is going to change. Okay, so just be aware of that. Actually, I think there's other slight differences, that this is partially transparent. Here we go, alpha is 0.9. So that's on the bars. That's better. Get that subtle transparency. I think they're possibly actually more transparent than that. Maybe not. And there you go. Okay. So the process for reproducing charts is really just breaking it down, right? Breaking it down into what actually matters. So get the basic chart up, or you get the geometries right, and then worry about things like order and axis labels and colors and stuff like that afterwards. Okay, but start by getting the basic chart up.